Welcome to another Mathologer video. Many of you will have heard of the Indian mathematical genius Srinivasa Ramanujan, largely self-taught, astonishingly original, died way too young 100 years ago, and so on. An incredible story. One of the things Ramanujan is famous for are these totally insane infinite continued fraction equations like the one over there. A completely unexpected connection between the three superconstants pi, phi and e. And just like most of Ramanujan's mathematics, this equation is super hard to make sense of, even if you are a professional mathematician. Luckily, there is still some more accessible Ramanujan magic to be mathologerized before I have to tackle that part of Ramanujan's legacy. In particular, there's this great anecdote featuring Ramanujan and an infinite continued fraction. And today's mission is to explain what's really going on in this story and what the infinite fraction is doing there. Okay, in 1914, Ramanujan's countryman and fellow mathematician Prasanta Mahalanobis was visiting Ramanujan at his rooms in Cambridge in England. Ramanujan was cooking a meal and Mahalanobis was passing the time reading the 1914 December issue of the Strand, a very popular illustrated magazine at the time. Fun fact, a lot of Sherlock Holmes stories were first published in this magazine. For example, this particular issue featured the latest Sherlock Holmes story, The Valley of Fear. The Strand also featured a regular puzzle column written by one of the greatest puzzle inventors of all time. I'm a real fan, Henry Dudney. It's 1914 and the First World War had broken out earlier that year. Dudney's puzzles in this issue of the Strand are woven into a story of some of the patrons of a village inn discussing the war. For example, one puzzle asks how this red cross here can be cut into 5 pieces that can be reassembled into the 2 smaller crosses. Nope, no continued fractions inside yet. Soon, promise. But can you do the red cross puzzle? If you can, post a link to your solution in the comments. But now let's look at the other puzzle, the one that Ramanujan's friend was pondering while Ramanujan was cooking away. This puzzle is set in Louvain, a Belgian city which had just made the war headlines. There's a man who lives on a long street numbered on his side 1, 2, 3 and so on, and that all the numbers on one side of him added up exactly the same as all the numbers on the other side of him. So all the purple house numbers add up to the same sum as the green house numbers. The puzzle consists in finding out how many houses were on the street and the number of the house in which the man lived. All clear? It's a tricky puzzle, but after a while Mahalanobis figured it out and then challenged Ramanujan to do the same. What happened? Yep, Ramanujan waved his magic wand or his magic brain or whatever and had the answer straight away. Pretty damn impressive, right? But what impressed Mahalanobis even more was that Ramanujan gave his answer in the form of one of these infinite fractions. And this infinite fraction not only gave the answer to the Strand puzzle, but also gave the infinitely many answers of a closely related and important super puzzle, a so-called Pell equation. Okay, so today we'll have a go at solving the Strand puzzle, understanding Ramanujan's solution, understanding why on earth people would bother with these infinite fractions in the first place, and at the end come up with a solution that even beats Ramanujan's, believe it or not. And the key to all this is the fact that root 2 is an irrational number and a curious property of A-size pieces of paper. Lots of ancient, beautiful and deep maths to look forward to. Okay, are you ready to solve the Strand puzzle together with me? Yes? Well, that's great. Then let's go. Okay, a street and a house with a special property. As usual, to get a feel for this problem, let's have a look at some small examples. So, can the street be 5 houses long? Let's first focus on house number 3, the house in the middle. Purple 1 plus 2 is 3 and green 4 plus 5 is 9. Since the sums aren't equal, our man is definitely not living in house number 3 on this street. Of course, with hindsight, That was never going to work, right? The house will definitely have to be past the middle of the street, since the numbers on the left are smaller than those on the right. So, how about house number 4? Close, but no banana. 1 plus 2 plus 3 is 6, which is not equal to 5. And that means that the street we are puzzling over is definitely not 5 houses long. What's next? Well, I leave it to you to rule out the tiny streets with 2, 3 or 4 houses. So let's go bigger and try the street with 6 houses. We still have a sum of 6 on the left, and now 5 plus 6 is 11 on the right doesn't work. And this time 1 plus 2 plus 3 plus 4 is 10 on the left and 6 on the right, too small, no dice. Okay, so forget about streets with 6 houses, on to 7. Left sum is still 10, and on the right we have 6 plus 7 is 13. Nope. Okay. 15 on the left now and 7 on the right. But wait a minute. Can you see it? 15 on the left and 7 plus what is 15? Well, 8 of course. 15 on both sides. So 8 works. Great. Problem solved. Not so fast. Remember, when you used to do word problems in school and your teacher would demand that you read every word. Well, welcome back to school. Let's read the puzzle again. It says, there's a man who lived on a long street. Yep, it's a long street, and I think we can agree that 8 houses is not long enough to be called long. So apparently, Dudney was after a different solution. Well, if you keep on searching, you actually do find another solution, this one here. And that's the solution Dudney was after? Well, no. Confession time. There's actually a bit more to Dudney's puzzle that I showed you. So, not only did you have to read every word like in school, you had to read some words you weren't actually given, like in a really mean school. Here they are. There. It also says that there are more than 50 houses in our street and less than 500. This means our solution up there is not Dudney's. There must be yet another solution. But wait a minute. Why did the maestro specify that the solution he's looking for is less than 500? Maybe there's an even larger solution. Well, it turns out that there are infinitely many solutions, and by stipulating more than 50 and less than 500, Dudney simply picked out one of these, so infinitely many solutions, of just the right difficulty. So how do we find it? You reckon it's a good idea to keep checking streets of increasing lengths? 50, then 51, then 52, and so until we hit the next solution without a computer by hand? Promise, not a good idea. Of course, there's a better way, which Mahalanobis would have figured out. But now comes the punchline. Ramanujan's infinite fraction method picks out all the infinitely many solutions all at once. Intrigued? Well, then it's time for a little algebra. So we're looking for the number of houses and the number of the special house. Well, let's call those unknowns. Wait, let's be really original. Let's call them x and y. What a surprise. So the purple sum on the left is 1 plus 2 plus 3 up to x minus 1. Easy, right? We've already encountered the formula for this kind of sum a couple of times in previous videos. Remember, it's this. Cool. And this sum is supposed to be equal to the sum of the greens. But the green sum is just the difference of two of those 1 plus 2 plus 3 sums. Can you see it? The green sum is 1 plus 2 plus 3 all the way up to y minus 1 plus 2 plus 3 all the way up to x. And so our formula for this sort of sum strikes again, twice. Okay, now some algebra autopilot to simplify this mess. Very nice. And as a quick check that we haven't messed up, let's sub in one of the solutions we found earlier. Okay, 6 squared is 36, times 2 is 72, and 8 squared is 64, plus 8 is also 72. Works! Great! Okay, what's next? Well, maybe play with the equation a bit, right? Written this way, the equation looks even nicer, and that x squared plus x squared equals y squared and a bit is somewhat reminiscent of Pythagoras. Is there any point to this? Well, reasonable to try, but sadly it doesn't lead anywhere. What else? Well, it's definitely tempting to solve for x or y and then start plotting and see where that gets us. But there's something else that's crying out to be done here. Maybe some of you will have guessed already. What we can do is some good old completing the square on the right. For this, let's just hit the Algebra autopilot button again. Did that help? At first glance, this looks more complicated than the equation we started with, right? But what's nicer about the new equation is that there is only one x and only one y, with a bit of noise around each. To suppress the noise, let's abbreviate the red by capital X and the green by capital Y. Now our new capitals equation is definitely much nicer, and importantly, if we find solutions to this new equation, then it's easy to translate them into the solutions of our original equation. How? Well, by substituting back for little x and little y, like that. Okay, so this is the equation we want to solve. Just a little shuffle to put it in its most useful form. There. Okay, someone like Ramanujan would see everything we've done so far in a flash, but even more so. Ramanujan also saw immediately that all solutions to this equation are contained in this special infinite fraction. What? What does that even mean? Well, that means he must be a genius, right? Well, believe it or not, that's not a rhetorical question. Before I really address this question, let's extract all those solutions out of the infinite fraction without worrying about the y, at least not to start with. To extract the solutions of our equation from the infinite fraction, we have to calculate the so-called partial fractions. Again, please just run with it. We won't worry about the y just yet. The partial fractions are the finite fractions that you get when you stop at one of the plus signs and zap everything from there on. So, to get things going, chop things off at the first plus. Okay, not much left. So the first partial fraction is 1. Which we can also write as 1 over 1. Nothing impressive yet, but let's keep going. Chop off at the second plus. 1 plus 1/2, that's 3/2. That's the second partial fraction. The third one is this, and that's equal to 7 over 5. And so on. There. And the denominator and numerators, they grow in size. A quick challenge for you. Can you guess a simple rule that relates consecutive fractions? Anyway, choose one of the fractions. Let's go for a really simple one. 3 over 2. Let's make 3 the y and 2 the x. 3 squared minus 2 times 2 squared, that's 9 minus 8, that's 1, works. The numerator and denominator solve our equation. Let's try the next fraction, 7 over 5. There. 7 squared, that's 49, minus 2 times 25. So 49 minus 50, that's minus 1. That didn't work. But we plow on regardless, and the next one works again. 289 minus 2 times 144, that's 1. Actually, what turns out to be the case is that every second fraction works. In fact, these fractions correspond to all the solutions to our equation in positive integers. And what about the other fractions? Well, they correspond to all the solutions of the companion equation with a minus 1 on the right. Pretty amazing, isn't it? Now, all that remains to be done is to translate these orange fractions into the solutions of the Strand puzzle. The translation rules were what? Well, these there. So to get the house numbers, the little x's on the left, we simply have to divide by 2, like this. And to get the corresponding numbers of houses in the streets, we subtract 1 and then divide by 2, like this. Nice. Here's our first solution. There's the second one. And of course, next is a solution between 50 and 500 that Dudney actually had in mind. Imagine finding the solution by trial and error. Scary, huh? I guess even just checking by hand that our street equation is satisfied by these two numbers would be way too taxing for most people who grew up punching buttons on a calculator. Before we move on, maybe ponder the 1-1 solution at the top. Can you make sense of this? Easy, right? Or not? Anyway, to wrap up, here's a summary of all the stuff that Ramanujan saw in a flash. Whoa. Now, there's no doubt that Ramanujan was an absolute genius. And there's definitely some genius mathematics in all this, especially that infinite fraction. And seeing all this at a glance is super impressive. However, that genius mathematics is actually not due to Ramanujan. And although continued fractions are a little forgotten, many mathematicians a century ago would have been familiar with this approach and would have followed something like Ramanujan's path to a solution of the problem. And so, great story that it is, Ramanujan's solution is not as amazing a mathematical feat as it may appear at first glance, and as it is often made out to be in the telling of the story. In particular, the equation that we are solving at the end is super famous, and all its solutions were first found a couple of thousand years ago. Also, any mathematician who has studied continued fractions will be aware that our equation is the simplest example of what is called a Pell equation. That is, an equation with some non-square positive integer in the place of the 2 over there. And these mathematicians would also know that all the solutions to a Pell equation are contained in the simple continued infinite fraction of root k. And indeed, our infinite fraction is that simple continued fraction of root 2. Well, that's all great. But I'm sure everybody else who has made it so far, you all won't be able to sleep tonight if I don't explain the connection with root 2 and where on earth this infinite fraction comes from. Well, don't worry. That's what I'll do next. So catch your breath, grab yourself a cup of coffee, and then let's get to it. So, what's a natural way to come up with that infinite fraction as a way to solve this equation, and what's the connection with root 2? Well, that root 2 is involved is actually easy to see. Let's tweak our Pell equation a little and replace the 1 by a 0. Then, autopilot. What this tells us is that if x and y were integer solutions of our tweaked equation, then the fraction y over x is equal to root 2. Cool. But of course, that's not going to happen. Since root 2 is irrational, such integer solutions cannot exist. On the other hand, going back to the original Pell equation, it's now also clear that if x and y solve that equation, then y over x will be approximately equal to root 2. And the larger the x and y, the better this approximation will be. Let's see how that works in practice. We already know the solution to the Pell equation, so let's compare the largest fraction here with root 2. Okay, in decimals, and that's really approximately equal to root 2. 5 decimals already. Pretty impressive, don't you think? Now, if you are a long-time mathologer viewer, this all may ring a bell, or 2, or 3, or forever. We already stumbled across the Pell equation and its solutions while proving that root 2 is irrational in the Marching Squares video a couple of years ago. Here are a couple of screenshots from that video. Well, that was a younger me. Do you see a difference? And we weren't just lucky then, it's actually quite natural to stumble across solutions of our Pell equation while playing around with certain proofs of the irrationality of root 2. Another one of these irrationality proofs is powered by the so-called Euclidean algorithm, an ancient mathematical superweapon with which many of you will be familiar. And now it turns out, and I'm guessing even most of you who are familiar with the Euclidean algorithm won't know this, infinite fractions like ours for root 2 are really just the Euclidean algorithm in disguise. Got it? Not only does the Euclidean algorithm lead to an irrationality proof of root 2, it is also at the heart of our infinite fraction. So there, in a nutshell, is one possible natural connection to the infinite fraction. In the rest of the video, I'd like to explain how someone playing with the Euclidean algorithm could naturally make these connections. If you think you've got what it takes to also survive this more challenging sort of masterclass part of the video, now is the time to don your mathematical crash helmets and seatbelts. And those of you who make it to the very end will be rewarded with a solution of the Strand puzzle that I think even beats Ramanujan's. I'll now take you on a wonderful journey of discovery. We'll start with some school maths, the Euclidean algorithm, head on to the irrationality of root 2, and wind up with Ramanujan's super duper solution of the Strand problem. Okay, you're all familiar with the Euclidean algorithm? No, maybe not. It's not taught as much now as it used to be. So just to be safe, here's a refresher. Take any two positive integers, let's say 38 and 16. Divide the larger number by the smaller with remainder. So in this example, 16 goes into 38 two times, and we're left with a remainder of 6. 38 equals 2 times 16 plus 6. Now repeat the process with the new numbers 16 and 6. 16 equals 2 times 6, that's 12 plus 4. Do the same with 6 and 4. Okay. Once more with 4 and 2. Okay. Again. Well, actually, 2 divided by 0 doesn't make any sense unless you want to enter the land of infinities. Well, I absolutely love infinities, but there is no need for them here, and so this is where things stop. All easy, right? But what's the point? Well, there are lots and lots of points. The point you will most likely have come across is that the Euclidean algorithm captures the highest common factor of our two starting numbers. There, that final 2 is the highest common factor of 38 and 16. And sure, in this case, the highest common factor is just staring at us. But what about two more intimidating numbers, such as these guys? Not so easy to spot the highest common factor now, right? But the Euclidean algorithm can easily click through those two numbers. There, 5 easy steps, and the highest common factor, 153, pops out at the end. It's also super easy to prove that the Euclidean algorithm always captures the highest common factor in this way. Anyway, back to our earlier example and back to work. Let's play around a bit with those 4 equations over there. Divide the equations by the blue numbers there and watch the magic unfold. Very cool, don't you think? A really beautiful fractional capturing of what the Euclidean algorithm is doing. There's also a really nice visual representation of the Euclidean algorithm that is lurking just around the corner. To see this, let's start with a 38 times 16 rectangle. Now, watch this. This shows that you can perform the Euclidean algorithm by repeatedly chopping off as many squares as possible, alternating between chopping horizontally and vertically. And the highlighted numbers are just the numbers of the different squares you chop off. 2 big blue squares, 2 aqua ones, and so on. And the side length of the final, smallest 2 by 2 square is the highest common factor of the starting numbers 38 and 16. Brilliant, isn't it? So next time you have to find the highest common factor of 2 integers, you know what to do, right? Mathematical MasterChef. Just cook up the corresponding rectangle and chop it into squares. Okay, so there's the result of the Euclidean algorithm on top and the continued fraction that we distilled from it. Now, what if instead of 38 and 16 we had started with half those numbers? 38 divided by 2 is 19 and 16 over 2 is 8. Then, except for the change in grid size, the top picture will look the same. And since the top picture stays the same, so will the continued fraction. So the continued fraction for 19 over 8 is the same as the one for 38 over 16. And of course the same would have been true if we had multiplied both the top and bottom of 19 over 8 by 2 or by any other number, right? Multiplying the top and the bottom by the same number just corresponds to scaling the rectangle, and so nothing changes in terms of the continued fraction. In other words, the continued fraction is really the continued fraction of the number 19 over 8 and not just that of a particular fractional representation of that number. This means that if we remove the grid on top, what's left is a complete visual representation of the continued fraction. Really incredibly beautiful. From all this, it's also pretty obvious that if instead of 38 and 16 we start with any 2 numbers whose ratio is a rational number, then the Euclidean algorithm will terminate after a finite number of steps, and the corresponding continued fraction will also be finite. But wait a minute. What if for some starting numbers, a and b, the algorithm does not terminate and we end up with an infinite continued fraction? Well, this would mean that a over b, the ratio of our starting numbers, cannot be rational, that this ratio must be an irrational number. So let's apply this trick to the obvious guinea pig, root 2. We need to think of root 2 as a ratio of 2 numbers. So let's start with a rectangle with aspect ratio root 2 to 1 and get the Euclidean algorithm going. Fun fact, it's no coincidence A4 and other A-size paper has these proportions. Okay, let's start cutting off squares. Calculate the corresponding continuous fraction and see where we end up. Well, that's the only square of the size that fits. This means the continued fraction for root 2 starts out with a 1. Next square, here we go. Another one. Okay, 2 of those squares, and so our fraction continues with a 2 like this. Next. Okay, another 2. And another 2. In fact, it looks like 2's will keep popping up forever. If that was true, we'd end up with the infinite continued fraction for root 2 that we encountered before, and we would have proved that root 2 is irrational. But how do we know that there will only be 2's in this infinite fraction and infinitely many of them? Well, that turns out to be pretty easy. To begin, after cutting off a number of squares, it's really hard not to notice that, apart from the 2's, other things repeat as well. For example, after we've cut off the first 2 squares, the blue one and one aqua one, have a look at the leftover white rectangle there. Doesn't it look very much like the starting rectangle, just rotated and scaled down? And in fact, that's true, and it's not too hard to prove. I'll leave the justification for this as a little challenge for you. Write up your proofs in the comments. Now, since the same shape rectangles appear over and over, the 2's they spit out keep appearing as well, on and on forever. Right? Cut off the next 2 squares and you're left with another white root 2 rectangle, and so ad infinitum. Okay, that's a beautiful proof, but still, this fraction monster equaling root 2 still leaves me scratching my head a bit. Maybe you too? For example, just looking at this thing, how would you go about calculating its value? Not clear at all, right? To get a better idea of what's going on, let's have a closer look at some of these partial fractions. As we've already seen, these partial fractions are really harmless and easy to evaluate. Okay, so let's chop things off right behind the yellow 2. To find the corresponding diagram up on top, we first throw away all the squares smaller than the yellow ones. There, infinitely many little squares gone. Now, we just rescale all the squares inside a tiny little bit so that the little indent at the bottom right goes away like this. There goes away. Then the value of the partial fraction is just the aspect ratio of this new rectangle. And as well, we can just read this aspect ratio of the diagram. If the yellow square is 1 unit wide, then the green is 1 plus 1 equals 2 units wide. How wide are the aqua squares? Well, 2 plus 2 plus 1, that's 5. And finally the blue square, 1 plus 1 plus 5 is 12. This means the rectangle is 12 units high and 12 plus 5 equals 17 units wide. And so our partial fraction is equal to 17 over 12. There. Of course, you can also just do the algebra and get the same answer. But isn't this absolutely marvelous? Thinking about continued fraction in this way really helps me and hopefully helps you too. It provides real insight into the true nature of these mysterious mathematical creatures. Here's another such insight. When we first form a partial fraction by truncating at a plus sign, it's not at all clear what the effect of that truncation will be on the value of the fraction. However, when we recognize that this truncation just amounts to smoothing out the little indent resulting from discarding some tiny squares, it's clear that the resulting rectangle will be very similar in shape to the original rectangle. Well, there's a smoothing action again for our example. There, smooth out. And just one more time, okay? There, smooth out, so nice. So it's really clear at a glance that 17 over 12 is a good approximation of root 2. It's also intuitively clear that the further down the infinite fraction we go before chopping off, the closer we'll get to root 2, the value of the complete infinite fraction. Well, life's good and we can stop scratching our heads. Saying that the infinite fraction is equal to root 2 really makes sense. Now, depending on what you include, this is either the third or fourth mathologer video dealing with aspects of continued fractions. And if you are a regular mathologerer, you may have heard me mention that those partial fractions are in some sense the best possible rational approximations to the full fractions. But that seems a very strange statement, doesn't it? How can any one fraction, such as 17 over 12, possibly be a best approximation of root 2, since all the partial fractions further down the track are much better? Well, let me explain. The obvious measure of how good a fraction approximates root 2 is simply the difference of the two numbers, right? The smaller the difference, the better the approximation. It's a no-brainer, isn't it? And then because root 2 is irrational, there is no best approximation in this sense. But we can approximate as well as we wish, with a difference as close to 0 as we wish. But really good approximations of this type come with a price. Both x and y will be huge numbers. So there's this other simple measure, a sort of value for money estimate for determining how good an approximation y over x is to root 2. That quantity down there, the left side of our Pell equation. That at least makes some sense, right? If y over x was exactly equal to root 2, this would make this expression equal to 0. That's not possible. And so since x and y are integers, the best way we can do by this measure is to score 1. And I've already told you that scoring 1 is actually possible and is achieved by our partial fractions in lowest terms. Remember? Half of our partial fractions have y squared minus 2x squared evaluate to 1. And the fractions in the other half return the value minus 1. In fact, there are no other superfractions of this type, and by the end of this video, the keen among you shouldn't have much trouble actually proving this. Anyway, if we were to dig down and tidy up more than we have time for today, we would discover that our partial fractions being best in the second weird way translates into the partial fractions also being best in a simpler and more obvious sense. Among all the fractions with denominators less than a certain number, it turns out, our partial fractions are closest to root 2. For example, 17/12 is a better approximation to root 2 than any other fraction with a denominator x in the range from 1 to 12. Maybe the clearest way to describe this measure of 17/12's bestness is to say that 17/12 is to root 2 what the super famous fraction 22/7 is to pi. As I said, there's a lot more to all this than we have time for today, but I hope this provides you with some intuition. Anyway, our partial fractions are really super nice and super important, and so let me finish up by proving to you some of the nice things that I only claim to be true so far, and then use all this to make a formula for the Strand puzzle that bests Ramanujans. Okay, are you ready to out-Ramanujan Ramanujan? All right, let's first pin down an easy way to generate all these partial fractions. To get the earlier partial fractions from the one of 17/12, just remove the two smallest squares, smooth out, and repeat. Here we go. Remove, smooth out, remove, smooth out. Okay, there. Remove. Well, not much to smooth out there, but anyway. Wonderful. So in this way, starting with one of the partial fractions of the infinite fraction, we've constructed all the earlier ones. And we've done so by successively removing the two smallest squares and smoothing out the resulting indents. Now, because of the nice periodic structure of the continued fraction of root 2, there is a second way of constructing those early partial fractions. Instead of removing the smallest squares, we can also remove the largest two squares. Here we go. Get rid of the largest square and the second largest square. And what's left is the partial fraction 7/5 placed on its side. Get rid of the largest two squares, and that's 3/2. One more time. 1/1. What's extra nice about the second way is that you really just have to get rid of the squares and no extra adjustment is needed. Also, running this construction in reverse, that is adding two squares at a time, we can construct absolutely all partial fractions starting with just this one square. Another thing that's very easy to glean from this is an easy relationship between successive partial fractions. There. If the sides here are L and S, then the sides of the next larger rectangle are, well, S plus L and S plus S plus L, which is 2S plus L. So this means that if the first partial fraction is L over S, then the next one is 2S plus L over S plus L. I guess that's the relationship that a lot of you will have guessed previously when I challenged you to do so. Now we have a proof. Now, starting with the first partial sum 1/1, we can use this formula to also successively generate all the other partial fractions algebraically. There. Feed that one in the front, spits out the next one, and do it again, spits out the next one, and great. Challenge for you, use this relationship to prove that our measure for bestness of approximation alternates between 1 and -1. It's an easy one, but a nice one. Okay, this is a simple relationship that will get us all those partial fractions easily. But we can do even better. Our relationship consists of two consecutive fractions. What's the next fraction? Easy. Just iterate this relationship, that is, plug the second fraction into itself. Wow, can you see it? There. So there in the numerators, you've got something like Fibonacci in action, right? To get the numerator of the third fraction, you simply have to add 2 times the numerator of the previous fraction to the numerator of the fraction before that. And the same is true for the denominators. Wow. There, 2 times the orange 3 is 6, plus the green 1 is 7. 2 times 7 is 14, plus 3 is 17, etc. And at the bottom, 2 times 12 is 24, plus 5 is 29. Brilliant! So both the numerators and the denominators grow in exactly the same Fibonacci-like fashion. The only difference is that the numerators start with 1 and 3, whereas the denominators start with 1 and 2. There. For the Fibonacci numbers highlighted in blue, there is this amazing general formula on the right, Binet's formula. Plug in 1, it spits out 1, plug in 2, it spits out 1, plug in 3, it spits out 2, and so on. One Fibonacci number after the other. I actually showed you how to derive this formula in the video on the Fibonacci sequence. Remember that video? Well, the hardcore ones among you will remember. Now, in pretty much exactly the same way, we can also find general formulas for our denominator and numerator sequences. Here they are. Pretty! And these formulas now straight away translate into general formulas for the infinitely many solutions of the Strand puzzle. What a wonderful solution, isn't it? Beats Ramanujan's infinite fraction? What do you think? Anyway, lots more amazing stuff I could mention, and I'm tempted to go on for a couple more hours. But maybe that's a good time to stop. Until next time.